Hello everyone, welcome to the numerical methods class. In this class we are going to continue on the numerical differentiation and integration, but now we are at chapter 20 and we will talk about the engineering applications of numerical differentiation and integration in the following slides. In engineering we use the numerical differentiation basically for functions again, but there are two or three cases that we are going to show in this slide. And usually the engineering involves characterizing the changes of variables in both time and space. So this time and space is important because we will be using these as the functions. And in the first case, when the change in time or space exists, differentiation can be required. So usually we are at some position, at some location, and we are changing the location by acceleration or changing our speed and going to another location. So in between we are spending a time or space basically. That's why to find the velocity, for instance, we need to take the differentiation of the position function, and to get the acceleration we need to take the derivative of the speed function. And these are usually dependent on the Newton's second law, which is shown as F equals m times a. A is acceleration, m is the mass of the particle or the object, and F is the force subjected to the object. So basically, if we have an acceleration, if we multiply it by the mass, we will get the force acting on the object. And in this, the change of position of an object in time is necessary. So because there is time, and with the acceleration we are getting a speed actually, we need the derivative of the functions. Second, laws governing the special behavior of variables are expressed in terms of derivatives as well. For example, in heat conduction, there is Fourier's law, and the Fourier's law of heat conduction quantifies the observation that heat flows from regions of high to low temperatures. So for instance, for one-dimensional case, we have a function of T, the temperature, in terms of X. X is the spatial location, actually, the position of the on the structure, let's say, for instance, and we get the heat flux by taking the derivative of T function with respect to the input, which is the position. And the derivative provides a measure of the intensity of the temperature change or gradient that derives the transfer of heat. The third case is similar laws provide workable models in many other areas of engineering, including the modeling of fluid dynamics, mass transfer, chemical reaction kinetics, and electromagnetic flux. So actually the differentiation is mainly important for any type of engineering area, specifically for these cases. Integration is also important in engineering, and that's why we need some numerical integration methods to be able to get the integrations. And we are going to show here three important examples. And usually the integration is mainly important for cases where the area under the curve is required. For example, a surveyor might need to know the area of a field bounded by a meandering stream and two roads. You can see here the stream and two roads, and we want to get the area of the field in between, and this area is basically found using the integration. If we know the stream data points, we can numerically take the integration underneath these data points, which is bounded by the roads, so that we can get the area. Another example is a water source, and a water source engineer might need to know the cross-section area of a river. Let's say this is the channel cross-section of the river. River is flowing in the third direction, and we just want to know the area or of the depth and the area of the water at this cross-section, let's say. If we know the data at the top point of the water, we can get the area underneath to get the area. In another example, a structural engineer determines the force due to a non-uniform wind against the side of a skyscraper. Here you can see that we have a skyscraper and there is a wind here, which is not uniform. So if we know the data or locations of the wind points, we can get the area underneath. Actually, if there is a straight like wind, let's say, and it's touching here on the skyscraper, or if this is a non-uniform wind, we can get the area here to be able to get the force due to the wind. Here also the function can be here, or the function can be the function of the soil or the bottom of the river channel, we can say. From that we can get the area as well. If we assume that water is just straight line and we know the function of this, then, or the data of the depths, we can get the area from there too. So there are different options like these in engineering that we can use integration, basically mainly for the area calculations. Integration is usually a summation of some points underneath of a function, and that's why it is very similar to summation operation. So for a continuous function, its integration is the collection of all data in a range. Basically, let's say this is a continuous function between a and b. We want to get the collection of all data in between. But if we have a discrete data, so we don't have a continuous function, we have just points, as you can see here. Then the collection of data is the summation. So we sum these points basically to get the area again. So summation is shown like this, and the integration is also a summation, but because it's continuous, it's in between two ranges and a function. And that's why the integration is basically the summation for a continuous function. And this analogy between integration and summation can be shown for mean operation. So mean is actually the summation of these points divided by the number of points. We showed this in the statistical chapter. And in the continuous function or data, we have mean again. So we take the integration and divide it by the range to get the mean. So this is the same as this, but here we have discrete points. Here we have a continuous function. And this is used for many applications. For instance, we want to calculate the center of gravity of irregular objects in mechanical and civil engineering. In statics and dynamics classes especially, we showed you that the center of gravity, if we have irregular objects, we can use composite calculation of the parts. We separate them into some pieces to get the center of gravity or moment of inertia also for irregular objects. We just use this discrete option, sum, instead of taking the derivative, the integration. Also, another case is to determine the root mean square current in electrical engineering. This is not really in our mechanical engineering area, but we can get the root mean square current in electrical engineering as well. So these are two examples that we use these discrete points especially rather than the continuous function. And in the mechanical engineering area, especially center of gravity, moment of inertia, the area, these are determined using this summation instead of continuous functions for irregular objects. Usually we have irregular objects and we use this. There are other numerical integration applications as well, and these are given here. And before that, let's read the first sentence. Integrals are also used to evaluate the total amount of given physical variable. For example, the integral may be evaluated over a line, an area, or a volume. So we learned this especially in the center of gravity calculation or center of mass calculation. And here, for instance, the total mass of a chemical reactor. So the mass is basically concentration times volume. This concentration is the density, we can say, and times volume. And we need to get the volume. To get the volume, we need to sum all the particles, or concentrations times delta V is the mass of each particle in a volume, or in a part, let's say, in a reactor. And if we sum them all, it gives us the mass. If this is a continuous function or continuous part, let's say we have infinite number of molecules in a solid part, for instance. So we sum all the particle masses, and because it's a continuous case, now we are using the integration rather than summation. And because we are focusing on volume, which is in 3D, we have a 3 integration, as you can see here. The second case is actually just finding the area rather than the volume. So the total rate of energy transfer across a plane, for example. The flux in calories per square centimeter per second is a function of position. So if we know the flux, we get the 2 integration to get the area underneath to obtain the heat transfer. And if here the function is not continuous and we have discrete points, then we sum them to get the heat transfer. Second is was the area. The first one was the volume, and the third one, as you will understand, will be a line actually. So volume, area, and line. In line we have only one integration. For example, total mass of a variable density rod. Rod, we can assume that it's only one-dimensional. There is only x length with constant cross-sectional area. We only have the density and area is constant. So if the area, the cross-sectional area is constant, then we can just simply take the integration of the density to get the mass. And if the density is changing with x continuously, then we can get integration. If we have discrete particles, then we get summation of this. So these are basically the 3 applications in 3D, 2D, and 1D, and we can use integration for these as well. We also use the integral to evaluate the rate equations. For instance, we have the velocity of a particle, and it is a known continuous function of time, vt. And dy dt gives vt. Vt is velocity, y is the position. Taking the derivative with respect to time, it gives us the velocity. And the total distance y traveled by this particle over a time. So when we have the velocity function, basically, take the integration, we get the distance y traveled by this particle. And this area is the distance. Now take the derivative of this, which gives us, actually this is the area gives from 0 to time 5 this distance. So distance is increasing to 5 like this. And this area value is here. Actually it's delta y, we can say. From 0 to delta y, it becomes y value. 2 cases when the numerical methods are required. The first one is when the functions to be analyzed are simple, the integration can be obtained analytically. We said that already in the beginning of the previous chapter actually. If we have simple functions, we can simply get the integration analytically. However, it is difficult or impossible when the function is complicated, which is typical in realistic engineering applications. In reality, in engineering applications, we usually don't have the function, or it's difficult to integrate. That's why the underlying function is often unknown and defined only by measurement at discrete points, or it's difficult. Then we use numerical integration. For these both cases, if difficult or impossible, if there is a function or no function, but there are measurement data. For both cases, we has to use the ability to obtain approximate values for derivatives and integrals using numerical techniques. So these numerical techniques will be important in engineering. And if we have the simple functions, we can simply use analytical integrations and derivations. Here some commonly used derivatives for sine, cosine, tangent, natural logarithm, exponential. And these simple functions, we have simple derivatives, as you can see here. And also for integrations, simple integrations, you can see here. For this kind of functions, these are simple, considered as simple, so you don't need to use the numerical integration, just use analytical integration we showed here. However, many functions are too complicated. Apart from these, there are many other functions which are too complicated to be contained in such tables. We cannot include them into these tables to solve analytically, and for them the numerical integration methods are used without knowledge of the rules. So let's use numerical derivatives or integration methods to solve them. And this is the end of chapter 20. Thank you very much for listening. We actually talked about the engineering applications. It's in chapter PT6 in your book, PT6.2 and 6.3. You can check them in your book to have further information. And thank you very much again. See you in other classes.